So what we didn't get to, and it's kind of the last thing, is the parallel combination of the RLC network. All right, where it'll say something like VC at time equals 0 is not equal to 0. The current through the inductor at time equals 0 is not equal to 0. Because if they were both 0, well then nothing would, it'd be 0. All right. Now, yeah, I guess it's possible to I could do a mesh here and a mesh here, but I think it's a lot easier with nodal and with taking the Laplace transform of the elements. All right. So I'm just going to redraw it here. Okay. So we have R, L, and C. And I want to take the Laplace transform of that. And since pure resistances have no energy storage or no differential, aren't modeled by differentiating or integrating over time, it doesn't change in the Laplace transform. But how can I tell that I have taken the Laplace transform? Well, if I just put, instead of L, I put SL, because ZL equals SL. ZR is R, and ZC equals 1 over SC. Now, I'm going to leave it at that for right now. So I'm just going to try to draw this a little bit bigger. So we can see what's going on. So let's assign the currents. Let's assign the voltage drops. And yep, you might think it a little bit odd that we have a node here and current is flowing out of it. Nothing is flowing in and nothing is flowing out. I think the reason why it's done this way, rather than, well, there's charge stored up here, current is going to be flowing into here and into here, is I think it just makes the math easier when you do the first nodal equation. All right. So because it's all leaving, right, I can say, and I'm going to use capital for the S domain for the current. All right. So I R plus IL plus IC equals 0. Just to remember, when I'm using the capital, I'm leaving off the fact that it's a function of S, which is a complex quantity that we'll find out later. So there's really just one node. I call it 1. And the reference node, which is ground. So what's this current? Well, it's the voltage at node 1 divided by R. What's the current IL? V1 divided by SL. And we have V1 divided by 1 over SC equals 0. All right. So I'm going to bring out V1, and I have 1 over R plus 1 over SL plus, and rather than leave it 1 over 1 over SC, I'm just going to say SC equals 0. All right, so in these questions, the voltage across the capacitor and the current through the inductor are non-zero. So it says it right there. So V1 equals VC in this case, and so it's not 0. So in order for this equation to be 0, it can't be V1, right? So we just ignore it, right? And it makes it a lot easier to then find the roots. So I'll just rewrite it, 1 over R plus 1 over SL plus SC equals 0. Now, ultimately, we need to find the roots of this equation to determine the behavior, all right? But in order to, we need to find roots. We need the quadratic form, right? So while this is a mathematical equation and you could find the roots, I'm sure, some way, we really want something like A S squared plus B S plus C equals 0. Or, you know, maybe, we're more familiar with this, right? So we have to manipulate it. And you might wonder, like you might make a mistake, but eventually you kind of know the answer, so you know which way to start manipulating the math, right? A lot of times when you're doing a derivation that's never been done before, you make a lot of mistakes, realize you're wrong, and then go back, right? So I had a question, is this EE101? Yes, it is. And I actually have a webinar. You're enrolled?
Yeah, I just added it.
Okay, so I just sent out an email to this webinar link. You don't have to follow it. I do save these on YouTube, just to let you know. Okay. So in order to get S squared, right, well, I'll multiply through by S. That'll cancel that out. That'll make that S squared. I also like to make sure that A equals 1. It's not mathematically incorrect not to have it, but just trust me, please, that it's an easier way to go. So I'm going to cancel out the C there. So when I multiply all that through, I get 1 over RC times S plus 1 over LC plus S squared, right? And yep, it's just like my convention. I always like to put it into this standard form, right? And sometimes the way you can think of it is, you know, at work, you'll have standard operating procedures of this is how we do something here, so that you don't spend a lot of time interpreting things. Like it could, you know, just as a quick aside, it could be something like whenever we draw op amps, the minus is going to go here, the plus is going to go here, and we're going to draw these resistors straight across, right? So that we all do it the same way, and so it speeds up communication. Oh, sure, if I drew it upside down or face, and like the signals will always go from left to right, right? It's not wrong the other way, but it just might take more time for somebody to understand what you're talking about. All right, well, now we can use the quadratic equation here. The roots of S, and there's going to be 2. Because this is squared, we have 2 roots. And it's going to be minus b plus or minus square root. And that's where we get 2 of them. B squared minus 4ac divided by 2a. Now, if you really need the whole number, you know, what is the root? And you have to know it. Oh, you have to calculate the whole thing out. But sometimes all you need to know is what's going on in here, right? Because there's 3 main behaviors. Overdamped gives us e to the minus t alpha 1, e to the minus t alpha 2. There's 2 exponential decays. That means there's 2 real roots, no imaginary. Well, what would 1 over RC, that's a real number. A is real. Where could we get an imaginary number? It can only come from here. What will guarantee? So if b squared is greater than 4ac, then we get 2 real roots guaranteed. Okay? Well, in this case, that means 1 over RC squared greater than 4 LC. And if you look at the problem and it gives you so many ohms, so many farads, so many henries, so many farads, right? If this squared is bigger than this, it's overdamped, and you're going to get. Now, I think in the problems instead of alpha, it might use betas, but you're going to see 2 exponential decays with 2 different constants here, right? Now the other. So that one's it's almost like a first order, except instead of 1 exponential decay, you have 2. All right, but what if b squared equaled 4 AC or 1 over RC squared equaled 4 LC? Then you get minus b plus or minus the square root of 0. So there's 2 roots here, right? But where with the overdamped case, you're plus some number, minus some number, That was 2 distinct. But now we have b divided by 2, and you might say, well, it's 0. It doesn't affect it. Right, but the fact there are 2 there, and it does change to where you get this linear. Yeah, you still have exponential decay, but you'll have this linear term there. Okay? So that's 2 repeated roots, meaning it's just, there's 2 of them, they just happen to be equal to each other. So it's not a first order, there's still a second order circuit. All right. If b squared is less than 4ac, we're going to get minus b 2a plus or minus some number times j. Just sometimes I forget, j equals I equals square root of minus 1. All right. But we tend to use I for current, so that could be confusing, so we use j for an imaginary number. So what you'll have is you'll have a real plus some imaginary number, a real minus some imaginary number. So we have 2 complex roots. And that means we're going to have some kind of oscillation times some exponential decay. The thing about imaginary numbers is, in electrical engineering, that tends to mean we're storing some kind of energy. It's also closely related to sine waves. So whenever you see an imaginary number, it's usually energy is being stored and there's some sinusoid there. All right. Now there is another case that can crop up, is but I'm going to draw out the whole quadratic equation for that. All right. Now sometimes R is very, very small and can go to 0, right? So what would happen? Well, physically, you would replace that resistor with a wire. Oop, and that's an inductor. So now, if this resistance gets really small, that means this node and this node is connected together. There can be no voltage built up in these devices, and so nothing works. Everything is 0, right? Which isn't a 101 choice, but I'm telling you that for completeness. Now, what if R, in this case, goes to infinity? All right. So r goes to infinity, IR goes to 0. As this gets bigger and bigger, as no current goes through there, it just disappears. And you get this. All right. Let's go back to our quadratic equation. And so if r goes to infinity, this goes to 0, this goes to 0, we have plus or minus a minus number. There's no real component. It's all imaginary. You get an oscillator, right? The e to the minus, you have like cosine omega t times exponential decay. But if this is 0, right, then this is 1 the whole time, and it just oscillates, right? Now, there's a difference here. That summarizes what we just said. Over here, if r equals 0, we actually get this circuit, which we actually is this, which means it's cosine. R equals infinity, gives us an open circuit. And then everything is 0. Okay? So for series RLC, we had s squared r divided by ls plus 1 over LC equals 0. For parallel RLC, we had s squared 1 over RCS plus 1 over LC equals 0. Here, r divided by L squared greater than, equal to, or less than gives, for LC, gives over critical under. For this, it's 1 over RC squared greater than, equal, less 4LC over critical and under. In the series case, R goes to 0. We get cosine. Over here, r goes to infinity, we get cosine. Then there's one more case I think that they have, is that if r is less than 0, if r is less than 0, instead of 1 over minus rc, the roots are positive, gives exponential increase. And here, it's r over L, same thing. If r is less than 0, this negative becomes a positive, we get E exponential increase. So anyway, the question, right, in the circuit, R is 4, L is 192 microhenries, C is 3. The initial voltages are not 0, and neither is the current. Are we going to have a pure cosine, exponential decay, because there's 2 exponents. We have exponential decay times a cosine, right? We have exponential increase times a cosine, and then we have a linear times an exponential decay. So this would be over, that would be critical. No, this is critical. This is just out of control, it doesn't have a name. This is under, this is overdamped, And this is out of control. It doesn't have a name. All right. Just not quite sure why this isn't copying everything. Anyway, so you're on the 101 exam. It's kind of hard to remember, and I actually don't suggest you memorize that chart. You're just going to forget it, right? But we've already derived it for today. I would rederive it out the way I've done it. I would then, you already know. You already know the quadratic equation, right? You just got to find B. You got to find 4AC bigger than, over, equal, crit, less than, under, right? And if this is infinity, it's going to oscillate. If it's negative, it's going to be the exponential increase one, all right? I see a lot of people try to backfit this into alphas and omegas. No, just do it the simple way. So in this case, b squared it's the parallel version. It's 1 over RC squared. So we have 1 over 4 times 3u squared. And we have 4 divided by LC equals 4, 192 microhenries and 3 microfarads. All right. So 1 divided by 4 divided by 3 micro. One over that. I messed up. 4 times 3. All right, 8.3 repeated times 10 to the 4th. And you know what? I didn't square that. So I think you saw me make a mistake right then. These are relatively close. Having something to the 4th and something to the 9th, that wasn't like normal, okay? So anyway, they're equal. That means it's critical. So that's just an everlasting sinusoid. Two exponential decays, that's overdamped exponential decay times a cosine under. exponential increase times a cosine, linear times exponential decay. Bam, it's right. So really, we've hit, you know, this is the bank, right? It says it right here. Choose 6 of these randomly and then give them random numbers, okay? So we've got first order, switch is opening, RC. First order, RC, switch is closing. RL, switch is closing. RL, switch is closing. RC, switch is closing, right? All these various versions. Then we have series, RLC, right? And what it is it looks like it's all the same question, but some of them will always be over, and it's going to randomly select like over, under critical damped problems, right? Then we have the parallel. We have a few more of those. And so we've kind of hit everything in the transient spot. And this is in EE101, we're going to learn a different way to solve these problems. Right now, we're kind of doing it in an intuitive way, sometimes with the Laplace transform. But in 110, we're going to really stick to the Laplace transform and find the thing is for those RLC, for those first order problems, everything, the input, they're all steps of one way or another. Something turns on right away or something turns off right away. But what about signals that are a ramp? What about signals that do this? What about signals that do that? How does, right? We have an RC circuit. Okay. We've done a step response of that. How does this respond to a step response? Oh, 1 minus e to the minus t, right? But how will that respond to a ramp? How will it go to an exponential? How to some arbitrary waveform? Well, we need then we really want to get to the Laplace transform of that. But when we're learning it, and like, you know, some of these are right on the first homework assignment, you'll see this, we'll be learning a different method, but you'll say, well, I can always check my work because I remember that they're all first order, you know, all of these, this kind of problem that I've shown all have kind of that. Then when we get into the second order, yeah, we have over, under, and critical damped, and then we have ways the circuit can be out of control. All right, so it is pretty important. That's why, yeah, there's 6 questions on it. All right, I think now the next thing is, it looks like it's circuits, and it is, and it's all impedance, but it's really every single one of these is manipulating imaginary numbers to where you can do it, maybe not in your sleep, but you're not going to struggle with it. Because in 112, they use imaginary numbers quite a bit. 110 too, but talking to students, they said 112 uses it more than that. And yeah, there's the op amps. The reason why I spent so much time on transients is when I look at the exams, yeah, a lot of people, that's where a lot of mistakes are, right? Then, yeah, maybe a lot of them come up in the op amps. So I don't know, yeah. Then the next thing that people struggle with are the op amp problems, right? But I thought next week we could just maybe spend 1 week on the imaginary numbers. What I did last semester, though, oh yeah, most people got the Laplace stuff. That's usually right. And then the RMS, most people are getting that right. It's kind of rare, right? But here's some as well. So really, then what I started doing is I just started giving, all right, I'd make up an exam on transients and would just, okay, we're going to spend an hour, do 6 problems in transients. How do you do? We'll do that more, I think, towards the end. You can always go online and do it yourself. I know you're busy with 118 and all your other classes, right? But I really want you to pass the final exam because you kind of, I mean, if you don't pass, okay, you can take it, but it makes it look like the money we spent here wasn't worth it. Okay, you know, if it now, yeah, you learned something, but you passed it eventually. But if you pass it on the final exam time, well, then you can register for 110, 112, excuse me, and 110 lab right away and get the section you want. Okay. Any questions? All right. Okay. All right, well, then we'll end it early.